Well, welcome and hello. This is the video on inverse trigonometry. And in this video, I'm going to assume that you've already done some sort of lab or exploration about inverse trig functions like inverse sine and inverse cosine and inverse tangent. All right, so we're going to jump right in and talk about how to actually find values for those functions. All right, so we got 6 examples. They go relatively quick, and so we'll not have too much to deal with there. So our first inverse trig function is what we call inverse sine. All right, so the idea is that in an inverse function, you switch x and y. However, sine is not a one-to-one function, so we end up with this little piece of a function right here, which is our inverse sine graph. As you notice, all right, some key points that it goes through is -1 comma -2, or negative pi over 2, excuse me, and that's because sine of negative pi over 2 is -1. And it also goes through 0, 0, because sine is 0, 0. And then sine of pi over 2 is 1, so inverse sine of 1 is pi over 2. So notice the x and the y coordinates are just switched. So the restricted domain is everything from negative pi over 2 to pi over 2. We can call this function either arcsine of x, that's explained in part of the lab, where arcsine comes from, but it basically comes from our arc length, or sine with the -1 right here in between the sine and the x. All right, that's not 1 over sine of x, this is inverse sine of x, and trig functions have their own unique notation there. But what this means is y equals arcsine of x if and only if x equals sine of y. In other words, what we're doing is we're given a ratio, that's what we're plugging in, and then we're going to get the angle that goes along with the ratio. Whereas when we did regular sine, we had an angle and we came up with a ratio from that, or a coordinate on our unit circle. So for this arcsine function, the domain is -1 to 1 because that's our possible range for our sine function, and then our outputs, our range for our arcsine function is negative pi over 2 to pi over 2. All right, then we have inverse cosine. So the function looks a little something like this. This is a piece of the cosine function where x and y have been switched. Notice it goes through -1 comma pi. That's because cosine of pi is -1. 0 comma pi over 2, and then 1 comma 0. So these are all the coordinates with our x and y flipped. However, we need to restrict our domain because in this case, we need to make sure that we make it a function. So it needs to have only a specific range of outputs. So we can call it y equals arc cosine of x, or cosine to the -1st of x. This is called inverse cosine. And that means y equals arc cosine of x if and only if x equals cosine of y. Notice how I switched my x and my y. The domain of this new function is -1 to 1, and the range is 0 to pi. So these are the only angles that we're going to output are the ones from 0 to pi for inverse cosine. And finally, we have inverse tangent. You'll notice it looks like the tangent graph that's been flipped on its side. Goes to the points -1 comma -pi over 4, 0, 0, and 1 comma pi over 4, among other points. All right, and this is only restricted to the domain -pi over 2 to pi over 2 for the tangent function. So we can call this one arctangent or inverse tangent of x. Y equals arctangent of x if and only if x equals tangent of y. And so x can be any real number. Remember that tangent has a range of all real numbers. So the inverse tangent has a domain of all real numbers, and then our range is -pi over 2 to pi over 2. And this function actually does have a horizontal asymptote at y equals -pi over 2 and y equals pi over 2. Okay, so some examples here. Let's find first what is inverse sine of 1/2. What this statement says is find the angle in between -pi over 2 to pi over 2 so that sine of y is equal to 1/2. So I want you to notice on here on this unit circle that I've drawn, and I will do throughout all these examples, I also included the negative versions of the angles in the 4th quadrant. So we got -pi over 2, which is the same coterminal angle as 3 pi over 2, -pi over 3, -pi over 4, and -pi over 6. So remember, our outputs for our inverse sine function only need to be between -pi over 2 and pi over 2. Otherwise, it's not going to be a function if you get multiple outputs. So we've restricted our range of values that we give as outputs. So I need to find where sine of y is equal to 1/2. In other words, where's my y coordinate on my unit circle 1/2? And that's at pi over 6 right here. So our answer is pi over 6. What is arcsine of -1? So remember, arcsine is equivalent to saying inverse sine, as we did in part A. So we need to find the angle in between -pi over 2 and pi over 2 so that sine of y is equal to -1. All right, so I'm looking at my unit circle on the right half where my y coordinate's -1. That's all the way down here. And we want to give an angle that's in between -π/2 and π/2, and that's just -π/2. We do not say 3π/2. We do not say anything bigger than that, like 7π/2. All right, we want one output, and we've restricted our range to be between -π/2 and π/2, so we give this answer right here of -π/2. That's it. No other answer. What about inverse sine of -3/2? So we want to find something on the right half of the unit circle, right, where our sine is equal to -√3/2, and that's -π/3. So again, one answer, not 5π/3, but -π/3. It fits in that range. What about arc sine of 3? We want an angle so that sine of y is equal to 3. Well, if you know anything about the unit circle, you know the y only goes from -1 to 1, so there's no such angle. 3 is not a possible sine value. What about inverse cosine? So inverse cosine of √3/2, looking for an x coordinate, right? So that our cosine is equal to √3/2, and that happens to be at π/6. So this is all about finding the angles that correspond to these cosine values. Arc cosine, remember that's equivalent. We want arc cosine of -1/2. So remember from the lab and from what we just said, our restrictions for cosine and arc cosine, our range needs to be between 0 and π. So sine takes place on the right half of the circle, cosine on the upper half. So we need where cosine is equal to -1/2, and that's at 2π/3. What about inverse cosine of -1? All right, that would be at π. That's where our x coordinate is equal to -1. And then what about arc cosine of 0, the angle in the upper half of the circle, so that cosine is equal to 0. And we look and we find that's at π/2. All right, finally, tangent. What about arc tangent of 0? We want an angle in between -π/2 and π/2, so that tangent of y is equal to 0. So this will be a line where our slope is equal to 0. All right, our angle has a terminal side slope equal to 0, and that's at angle 0. So hopefully on your unit circle, you've already drawn our common tangent values because they're going to be coming up frequently. What about arc tangent of -1? We want the angle so that tangent of y is equal to -1. This is where x and y are the same. The restrictions are going to be on the right half of the circle here. So that's at -π/4, where x and y are the same values, but one's negative and one's positive. So it's -π/4. And then arc tangent of -√3, we want a really steep slope, all right? That would be at the π/3 family, all right? And whoops, sorry about that. That's a typo. So arc tangent of -√3 is -π/3, which is this angle right down here. All right, so what do graphs of transformed inverse trigonometric functions look like? I'm not going to have you do too much with this, but I do want you to get the idea of what these graphs look like. All right, so for example, in blue here on the left, we've got arc sine of x. But what if we did arc sine of 2x? Well, you have your calculator or Desmos to help you out with this. But basically, it's the same idea. We've had a horizontal compression by a factor of 2, so it smashes the graph, all right, so that it only falls between -0.5 and 0.5. All right, so the x values decrease there. Arc cosine of x/3 versus arc cosine of x, which is in the blue. Notice that this stretches the graph out by a factor of 3 here. All right, so the same sort of transformations that we saw before. All right, we're going to talk about this more in class, but one of the things that we'll be looking at is what happens when we do compositions. That's when we plug one function into another. And remember that if we compose an inverse and its function, we should end up with x. And if we do f inverse of f of x, we also end up with x. That leads to some rules that are specific to trig functions depending on their domain and range. And the rules look a little something like this. So sine of arc sine of x is equal to x, and arc sine of y is equal to y, as long as x is between -1 and 1, and y is between -π/2 and π/2. In other words, we're finding that restricted values for our angles that we did on the previous slides, and then our range for the sine functions here. So we're going to have the same things be true when we compose a function in its inverse, all right, but only on specific values. Same for cosine of arc cosine of x, that's equal to x, and arc cosine of y, these are inverses, that's equal to y, and that's between 0 and pi for the y, and -1 to 1 for the x. And then if x is any real number, and y is between negative pi/2 and pi/2. This is our restriction for the arctangent outputs. Then we know that tangent of arctangent of x is x, and arctangent of tangent of y is y. As an example for this, let's run through a couple of these. If we want to find inverse tangent of pi/6, pi/6 is an angle between negative pi/2 and pi/2. That's our restriction for the tangent function. So right away, when we compose a function that's inverse, we should just get pi/6. Same thing here. If we started out with sine of inverse sine of 1/2, all right, notice that inverse sine of 1/2 is where sine is equal to 1/2. So that's at pi/6. And sine of pi/6 is just 1/2. So the same thing happens here. 1/2 is a value between -1 and 1, so it works for the domain for inverse sine. Now, let's try this. If we do inverse sine of 5 pi/6, notice 5 pi/6 is not within the right range of values for our inverse sine. All right, so we need to evaluate this by hand. So we say sine of 5 pi/6 is 1/2. All right, so the inverse sine of 1/2 is actually pi/6. So what this does basically is puts 5 pi/6 into a range of values that match where sine is equal to 1/2 in our restricted domain. All right, last thing here. So what happens if we wanted to do tangent of inverse sine of 3/5? All right, so notice we got two different types of functions here. Well, there should be no problem. We've talked about this earlier in the year. So when we say inverse sine of 3/5, what we're saying is find me the angle that gives me sine equal to 3/5 if we reverse this back. So sine and inverse sine are inverses, of course, of each other. So going back to something we did earlier in the year, this means that sine of y is equal to 3/5. And if we think about this as being some part of a triangle, going back to your geometry days, that means opposite over hypotenuse was 3/5. So I drew a little triangle over here with the angle y. All right, and if our opposite side is 3 and our hypotenuse is 5, that means our adjacent side is 4. So when we draw a picture, it really helps us to see what we need to do. And we know that tangent of y is opposite over adjacent. All right, so the opposite side in this triangle is 3, the adjacent side is 4. So that means that this whole answer is equal to 3/4. All right, because we found the tangent of this angle that makes sine equal to 3/5. All right, so in summary, inverse trigonometric functions are the same sort of restrictions as regular inverses. They have to be functions too, and the same idea as a transformation applied to our inverse trig graphs. But remember, when we do inverse trig functions, all right, we have restricted domains and ranges to make these actual functions. And compositions can also have special shortcuts, or maybe they don't. Maybe you actually have to work them out. Thanks for listening. We'll see you on the next video.